Okay, so we were talking about this graph, remember? And we're saying how we believe it has tangent lines. We believe that those lines have slopes, but it's certainly a shame that we cannot find the slopes of those lines. What a shame. Seems like we should be able to, right? But the problem with this function, does anybody remember what makes this problem so awkward? Yeah, it's really almost impossible to isolate y. It's not a function, first of all. It's really three functions. So what a mess this is, right? But with that new tool, implicit differentiation, we can just start right away and differentiate even the stuff that has y cubed and stuff. So let's go and actually officially solve this problem. So this problem is asking for the horizontal tangents and the vertical tangents. Okay? So we kind of need to understand what that means. If you have a horizontal tangent, that would be a line like this, right? And slope would be 0, right? I see two of them. I think I know where one of them is. Where is it? At the origin. But the other one I'm not so sure about. I think it's somewhere between 3 and 4. If I had to guess, I don't know, 3.8, something like that. The other one's at x equals 0, no about a doubt it. No about a doubt it. Okay. The vertical line, some of you didn't catch that. The vertical tangents, there's one right there. I would say somewhere between 4 and 5 probably. And of course there's one at the origin. So I love how this graph intersects its own self. That's called a self-intersection, by the way. And also it has a horizontal and a vertical tangent in the exact same spot. That's kind of neat. Okay, so let's just get started on differentiating. So the first thing is to understand that you could just take the derivative of x cubed to be 3x squared. That's this one. But when we take the derivative of y cubed, we have to write what? 3y squared times dy dx. And if you don't mind, I'm just going to write 3y squared y prime. Because there's a lot of writing, and I'd rather not have to hassle with writing any fractions, looking objects. So how about just y prime there? And then minus, okay, be careful on this part. This is 9 times something, so we can leave the 9 here, but how do you take the derivative of xy? Isn't that technically a product? Okay, so we need the product rule here. All right? So we need the product rule applied to xy. So we would do the derivative of x times y plus the derivative of y times x. So that would look like this. The derivative of x times y plus the derivative of y times x. Okay, so on the AP test, what I've noticed is when they give us a problem that uses implicit differentiation, it is very common that they put this cross term in here with x, y. They want to see if you'll remember to use the product rule. And you should have seen it last time in the homework too. Wasn't there a problem with the tan xy? Okay, interesting. They love that problem. Yes?
If you just did it as a three-way product rule, would you get the same equation?
Yes. 9 prime times xy plus 9 times x prime y plus 9x times y prime. Yes. Just remember that 9 prime is 0.
Yeah.
Yes, 9 prime is 0. Okay, so this ends up being our answer, and now we need to try and get y prime by itself. Okay, so let's go and distribute the negative 9. So we have 3x squared plus 3y squared y prime minus 9y minus 9y prime x equals 0. I see two terms that don't have a y prime in them. Let's get rid of them. So let's add the 9y to the right and subtract the 3x squared to the right. That'll clean up the left side. All right. So I have on the left 3y squared y prime minus 9y prime x equals 9y minus 3x squared. And then I can factor out a y prime. which allows me then to divide both sides to isolate the y prime. So here's what my final answer is. Y prime is, and I love the symmetry on this answer, it's 9y minus 3x squared for a numerator, and on the bottom it's basically negative 9x plus 3y squared. So it's 3y squared minus 9x. You gotta love the symmetry on that answer. The top and bottom are very, very similar. Look at the graph. It's got some symmetry of its own, doesn't it? Okay, so no surprise that we have an interesting looking derivative there. It's an interesting looking graph. So now, what are we going to do? Well, if we want to find the horizontal tangents, we're going to want to set this equal to 0, because we want where the slope is 0. But if we want to find the vertical tangents, we're going to want to set this equal to undefined. See? What's true about the horizontal lines is they have slope 0. And what's true about the vertical lines is that those guys have undefined slope. So in other words, if we can find the roots of the numerator, we'll be able to get the horizontal tangent lines. And if we can solve the roots of the denominator, we'll get the vertical tangent lines. Okay, I'm expecting to get 2 of each. If I get more than that, I'm going to be very suspicious. That means that I may have needed to do some weird factor cancel type stuff on this stage. But I think I'm going to get 2 of each. Let's try it. Okay, so first, to find horizontal tangents, set the numerator equal to 0. So 9y equals 3x squared. Okay, I'll show you how I did that. I just basically did the numerator equals 0, and this leads me to 9y equals 3x squared. What do I do with that? Well, let's divide it by 3. It reads this, 3y equals x squared, or we could write it as y equals 1/3 x squared. In other words, I could divide by 9. What is that? Like, how is that an answer? It's not an answer yet, but remember the original given function or relation. It was this, x cubed plus y cubed minus 9xy equals 0. This was the given, remember? I'm going to substitute this y into it. So it's going to look like this, x cubed plus 1/3 x squared cubed minus 9x times 1/3 x squared equals 0. I'm going to try and solve this. It's a little bit intimidating, but it says x cubed plus, and this would be 1/27 x to the 6th, ouch, minus 3x cubed equals 0. This would normally scare me with that x to the 6th and all, but I think it factors. In fact, we have some like terms first. Let's deal with that. So we have 1/27 x to the 6th, and I can put the first and last terms together. And I can factor out an x cubed, so we don't divide by x cubed, but we can factor it out. And this isn't so very hard to solve. We have 2 possibilities. Either x is 0, triple root on that, or x is the cube root of 54. How did I get that? I just took 1/27 x cubed minus 2, set equal to 0. I added the 2 over, multiplied by 2, and cube rooted. Anyone have a calculator? What is the cube root of 54? You can just type 54 to the 1/3. Hey, I was right. The horizontal tangents were at the origin, and I predicted there'd be one between 3 and 4. Of course, I've done this problem before. So let's go back up and look at our graph. See our graph? Like we said, look at the 2 green lines. There's one at the origin, and there's one at x equals 3.8, roughly. Okay, now there's enough symmetry on this problem to where I feel like I could just assume there's a line of symmetry right there. I think the other two answers are whatever the y value of this is, that's the x value of this blue line. And whatever the x value of this blue line is, that's the y value of that line there. So you probably don't even need to set the denominator equal to 0 and solve it. What you need to do is get the y coordinate at this point, and then you'll know the x and the y, and you can just trade them, and that'll give you this point. I don't know if you can see that or not, but if I just found the x is 3.799. If I can get the y coordinate of this point, I'll know both coordinates. And then I'll just trade them, and that'll give me the coordinates of these 2 points. I mean, the 2 coordinates of this point. After all, if you switch x and y in this equation, nothing even happens, which means it's its own inverse. So if this is AB, that's BA, for sure. So what I'm going to do is I'm just going to go ahead and find the y coordinates for these two, and then I'll take the xy pairs and I'll just trade them around and I'll have all 4 answers. Okay, question?
Yeah, just switching the x's and the y's, if nothing changes, does that prove that it's symmetric to y?
Yes, it proves that it's symmetric to y equals x. Yes, that's right. Because when you make y equal to x and x equal to y, nothing happens. Okay, so let's go ahead now and find the y values for these. Okay, this is going to be a little bit tricky. But, okay, let's just try this. Let's do, there might be a fast way to do this, but I can't think of it right off the bat. Let's just go ahead and pursue it. We know x cubed plus y cubed minus 9xy is 0. Let's plug in the cube root of 54. Okay, so it's basically the cube root of 54 cubed plus y cubed minus 9 times the cube root of 54 times y is equal to 0. Okay, and this gives me 54 plus y cubed minus 9 times the cube root of 54 y equals 0. How am I going to get the roots on that thing? Well, it probably factors in some way, shape, or form, but I think I'm just more comfortable cheating. So I'm going to get out my calculator, and I'm going to find the roots that way. All right, so I'm going to go in here and clear out my pre-calc function from earlier. I'm going to type 54 plus x to the third minus 9 times 54 to the power 1/3 times x. Now, I'm typing x because I can't type y, but it shouldn't matter. I'm just going to try and get the roots of this expression, or this equation. So here comes a graph. Make sure I type that right. 54 plus x cubed minus, I typed a plus there, no wonder. There we go. Okay, graph. All right. Let's see. I see 3 y values, and my gut feel is that this point right here at the top of this path has an x value between 3 and 4 and a y value between 1, 2, 3, 4. I'm thinking it's right around between 4 and 5. So I'm going to go back to my calculator screen. First, I'm going to make sure I type that thing right. Can't type it wrong, and I'll give you the wrong roots. Going back down here. This is the tedious part. Oops. 54 plus x cubed minus 9 times 54 to the 1/3 times x. Okay, equals 0. So I'm interested in this point right here. That's the one I want. That's the y value I'm interested in. Okay, so let's go ahead and do that feature where we make the calculator find the root. So let's do second calc. Let's go to 0. That'd be this one. And let's go over to that furthest point on the right. The third root here. Okay, so we want that one. So we'll make the calculator find it. 4.762. 4.762. Okay, so the root I'm interested in is y is approximately 4.762. And now we can go ahead and answer the question. So the top of that graph, remember it did the loop-de-doo thing. The top point, make sure I drew that kind of right. Not too good. More like that. I'll start over. It's kind of hard to draw. This is called a folium, by the way. A folium. Folium. This top point is at 3.779, comma 4.762. So I believe that this point, I have very good reason to believe it, is at 4.762, comma 3.779. Okay, and so they had asked me for where the lines are. What does that mean when they ask, where are the lines? They usually are asking for the x-coordinate. They want the x's. Okay, so we have a vertical tangent. Let's do horizontals first. Let's do horizontal tangent at x equals 3.779, and the origin, of course. Okay, so these are the two green lines. And then vertical tangents are at, and then we'll just use the 4.762. So x is 0 and x equals 4.762. And that's the answer. It's a tough problem. It's a really difficult problem. So how is it that we did the problem again? We just used implicit differentiation. We got this really awkward answer, but we knew that if we made it equal to 0, it would give us the horizontal tangents. If we made it undefined, it would give us the vertical tangents. And I kind of cheated. I got that first point, and I flipped the coordinates to get that other point, because I could see the symmetry. And I could tell from this equation that changing x and y around would not make any difference whatsoever. Okay? All right. So that concludes the lesson for implicit differentiation.